Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a second video on a review for college algebra students concerning functions. In this video, we're going to talk about function notation, or review briefly function notation, and we're going to evaluate some functions. Again, just like the last video, the material here is completely review. You should already know all of this, so I'm going to kind of rocket my way through it. Let's start with the definition of function notation. The notation y equals f of x defines a function named f. This is read as y is a function of x. The variable x represents the input variable or the independent variable, and the variable y, or f of x, represents the output variable or the dependent variable. That notation, by the way, is not multiplication. I shouldn't have to say that, but some students still think it is. So if we say f of 2, this is not 2 times f. Just letting you know. Some people will chuckle when they see that, but because they think it's kind of a silly, they would never have thought of doing that. But I'm telling you, teaching for years, I see it all the time. So let's talk about evaluating functions. When you're given a function and asked to evaluate, you're going to replace the input variable in the formula with the value or expression provided, and then calculate the result. That is a weird how-to, so let's just see it in action. Here's a function, m of t. That's how you would read this, m of t. M is a function of t. That is equal to t to the 1/3 plus t to the negative 2/3 divided by t to the 1/3 minus t to the negative 2/3. And we're asked to evaluate m of 125. What we're going to do is replace the t here, and therefore all of these values of t, with the number 125. Now, there are actually two ways to tackle this problem, and it doesn't really matter to me which way you do it, but I'll do it the way I think most students would do it. M of 125 is equal to, and we start the fraction, and wherever you see a t in this original function, you're going to replace that with a 125. Now, as this is a review for college algebra students, I don't need to explain to you what those exponents do. This is going to be 5 plus 1/25 all over 5 minus 1/25. And this is a compound fraction. If you need to review simplifying compound fractions, or if you don't know what I just did here, you're going to have to look up a video on the laws of exponents. So let me just point at this and say laws of exponents. And here, if you don't know what I'm about to do, you'll have to look up a video titled Simplifying Compound Rational Expressions. As you move into functions, it is assumed that you know all this stuff, and there's no need to review, at least for the instructor to review all of this. If we did, we would spend our entire careers just trying to teach one topic at the beginning of a course and reviewing how to do everything that's required for that topic for the rest of the course. So we can't do that. I'm going to go ahead and simplify this by multiplying both numerator and denominator by 25. And we get 126 over 124. And actually what you should do at this point is simplify this fraction, because that's a prerequisite to whatever course you're currently in. So I just divided both numerator and denominator by 2. And that's it. That's as good as it gets. So that's us evaluating that function at 125. I did say there's another way to do this, but I'm not going to showcase it. I'm just going to say it out loud because honestly, nobody's going to do it. The way that another way you could have approached this is to simplify this statement first. But I wouldn't do that, honestly, just because I'm only being asked to evaluate this for one value of the input. If I was being asked to evaluate this function m at several values, I would probably start by simplifying this compound rational expression first. But that's probably something that we don't need to really worry about. Functions do not have to be evaluated at nice clean numbers, and often they are not. So you do have to get used to evaluating functions at irrational numbers. And this is a good example anyway. What we're going to do is replace all the values of the input, which is x here. We're going to replace all of those with 1 plus the square root of 2. When you do something like this, use parentheses liberally. I often say that, but it's so important that you do that. So f of 1 plus the square root of 2, well, we have that 3 times something cubed, and that something is no longer x, it is going to be 1 plus the square root of 2. Then we have this plus 4 times something squared. That something is no longer an x, it's a 1 plus square root of 2. Plus 5 times something, and again, that something is no longer x, it is 1 plus the square root of 2. And finally, we have 3. 3 is not touching an x, so it just remains as a 3. And at this point, your prerequisite ability to do arithmetic and multiply radicals should come into play. Also, you should note that powers do not distribute across addition, so don't do that. That's a bad no-no. I'll write this as 3 times 1 plus root 2 times 1 plus root 2 times 1 plus root 2, just to showcase my mindset, plus 4 times 1 plus root 2. And so what I did here is I actually already distributed this 5 across because there was no other multiplication happening there. Now let's go ahead and perform some binomial multiplications. I'll just multiply these two together and simultaneously multiply those two together. And so we got to this point. By the way, that 8 comes from just me adding this 5 and this 3. Now let's go ahead and clean up the stuff in parentheses first. After every single step, you should step back and say, okay, is there any arithmetic? And there is here. If there isn't any arithmetic, then you say, is there any algebra I should be doing? You just graduate up through how you learned mathematics. That's what you do after every step here. Now you can see that we still have a binomial distribution going on here. So I'm going to go ahead and multiply that stuff out. And we continue forward. I'm going to distribute this 3 right here through each of these items and then combine like terms. And actually, instead of distributing at 3, I decided to clean things up first, hop back and do some arithmetic basically. Now I will go ahead and distribute that 3. And there we go. Notice that it was a simple, well, I don't want to say simple, but the basic idea at the beginning was kind of easy to see. I'm just plugging in a number into our function. However, a lot of our prerequisite skills come into play when you start evaluating functions. You do have to do distributions. You have to multiply out binomials several times here. You have to know how to work with radical arithmetic. Any of that stuff you need to review. I highly recommend searching to review that material. You can see that in some of my video series, maybe binomial distributions or radical, simplifying radical expressions, stuff like that. And one last thing, anything other than this answer here is incorrect. So if you do not simplify down to this, it is just incorrect. You have to apply all your prerequisite math skills to get to a final answer. Now here's something that might be slightly new, even though it's in a review video. This thing right here is very important as you move forward in mathematics. This type of expression is called the difference quotient. It is not the focus of this video, so don't worry too much about memorizing that name or even the structure of it. However, it is super important. We want to evaluate f at a plus h minus f evaluated at a all over h for this given function. I recommend the first time you see something like this to take this in pieces. You know that you need f of a plus h. So I'm going to take our given function and just go ahead and separately evaluate what is f of a plus h. Well, if you plug a plus h in for x, it will become 2 over the quantity squared, where instead of x being squared, we have a plus h being squared. I'm not going to distribute that out. I think that's a terrible idea. Leave denominators factored if you can. The next thing I want to do is evaluate our function at a. Well, that's actually not bad. All you're doing is essentially just replacing every x value in this original function right here with a's. So really it's just going to be 2 over a squared. And we're going to take the difference of these two expressions here, and then we're going to divide that difference by h. So let's go ahead and just write out f of a plus h minus f evaluated at a all over h. And let's insert what we just computed here. F of a plus h, that's 2 over a plus h squared, as we've shown up here. F of a, well, that's 2 over a squared, as we've shown right there. And then this is all supposed to be divided by h. Now, the way I've structured my courses and my lecture video series is that you should have already reviewed how to simplify this compound rational expression. If you need to review that again, please do, but I'm just going to immediately multiply numerator and denominator by a squared times a plus h squared. And when I do that, I get a 2a squared minus 2a plus h squared, and that's all divided by h times a squared times a plus h squared. Again, leave denominators factored, but in the numerator, I would highly recommend factoring or distributing, whatever you can do here. And I think most students are going to do this, so I will go ahead and do this. You can write this as 2a squared minus 2 times a squared plus 2ah plus h squared. And this is all over h a squared times a plus h squared. You do this because you want to kind of condense or combine things in the numerator as much as possible. And notice something very special happens. When you distribute out that -2 to each of the terms in that trinomial, you find that 2a squared cancels the -2a squared, and you're left with this statement right here. Now take a moment to see if there's anything else you could do here. Like in that numerator, could you factor something out? And the answer is yeah, I could actually factor out a -2 out of both those terms and an h. When you get down to this part, again, take a breath and ask yourself, is there anything else that will simplify? Well, if you don't look hard enough, you won't see it, but those h's cancel beautifully. And that is actually the point that you want to get to. You want those h's to cancel. Now, if you look at this final fraction, there's nothing else that will simplify. And so we have completely written out that expression, which is f of a plus h minus f of a all over h. We've completely simplified that expression down to -2 times the quantity 2a plus h all over a squared times a plus h squared. That skill is going to pay you back, trust me, in the long run. That's a calculus skill that you need to have. Nobody's going to teach you how to do it in calculus. You have to learn it now. Also note, as I move through my lectures, if something has been taught before, I do not spend time reviewing that topic because, again, we would spend forever kind of digging back because you didn't learn something well enough the first time. I highly recommend that you go back to review videos if you struggle with simplifying compound fractions. That you should have learned a long time ago. Again, with the assumption that you already know pretty much everything you need to know about functions up to this point, and you've been exposed to that, now we're going to do a little bit more in the way of advanced evaluations of functions. Let's take a look at part A here. We're being asked to evaluate f at some variable input, k squared minus 1. Well, here's the function f up here. What we're going to do is instead of plugging in x, we're going to plug in a different picture. The picture we're plugging in is k squared minus 1. So normally, f of x would be something cubed plus 2 times that same something squared. But we're not plugging in x, we're plugging in k squared minus 1. So let's go ahead and simplify this down. Now I hope you don't mind, I'm going to rewrite this down below because I didn't really leave myself enough room. And again, as I kind of try to reiterate as often as possible, you should take a moment to breathe and take a look at things that you've learned in the past that you can apply now. For example, if I'm going to do this, a lot of people will multiply all this stuff out. I highly recommend that before you go multiplying and distributing things out, you look, do either of these terms have something in common? They both have that picture in common, k squared minus 1. So we're going to factor out a k squared minus 1 to the second power from both of these. This is our factoring prereq. And when you factor off 2 powers of k squared minus 1, this first term, you'll still have a single power of k squared minus 1 left over, which you really wouldn't write it like that. You would not even have the parentheses, but let's just leave that there just to showcase that we did that. And we'd have a plus 2 after we factored off a k squared minus 1 squared off that back end. Now I'm going to go ahead and clean this up. And that's as good as it gets. That is completely done. You may say, but well, hold on a second. Shouldn't I multiply things out? If you multiply things out, it will actually get uglier than this. So I highly recommend you leave it factored like this. In fact, you could technically factor this guy right here. It is a difference of squares. So I'm going to go ahead and do that. So I have something squared times k squared plus 1. That something, which I've highlighted in yellow up here, is actually k minus 1 times k plus 1. And using a law of exponents, we know that's going to be k minus 1 squared times k plus 1 squared times k squared plus 1. And that is actually completely factored, completely simplified. There you go. Now you should read the original problem to make sure they didn't say something like multiply everything out, which they didn't. So this is a completely simplified version of f evaluated at k squared minus 1. I do want to tell you that this is actually a lot easier to work with than if you multiply it out. For example, if somebody said I need to find out what k of 1 is, I could just plug 1 in for k, and I would get 0 times I don't care, because 0 times anything is 0. So it's very nice to have the factored forms here. They really do speed up computations. Now let's take a look at part B. Solve f of x is equal to 0. This is just a picture. F of x is equal to 0. I'm going to replace the left-hand side with what f of x actually is. So let's go ahead and do that down below. We're going to solve f of x is equal to 0, f of x being x cubed plus 2x squared. Now you're not looking at a function anymore, you're looking at an equation. Notice both terms in that equation have an x squared in common, so you can factor that out, and you're left with an x plus 2. Now you can say, well, I have a couple objects multiplying to become 0. That means either that first object is 0 or this second object is 0. That is, either x is 0 or x is negative 2. That is the solution to the question that was being asked, when is f of x equal to 0? F of x is equal to 0 at x equals 0 or x equals negative 2. Now we go to the part C here. Solve g of x is equal to f of x. Again, you're just dealing with an equation where you get to replace pictures. So f of x I'll replace with this picture, x cubed plus 2x squared. G of x I'll replace with this picture, which is 2x plus 4. I'll do that off to the right-hand side here because then I can see the equations. There's our goal, solve f of x equals g of x, and the way we're going to do that is substitute x cubed plus 2x squared for f of x, and substitute 2x plus 4 for g of x. I'll slide everything to one side, and I see that I have an equation with 4 terms. This tells me that I likely have to use factoring by grouping. It's not always going to be the case, but it is the case here. There are some very special cases where you don't use grouping on factoring like this, but most of the time it will be. So the first two terms, I'm going to factor out an x squared. I'll be left with an x plus 2. The second two terms, I'll factor out a negative 2, and I'll be left with an x plus 2. We know from our years of factoring that we can factor the x plus 2 off back, and we'll be left with x squared minus 2 times x plus 2 is equal to 0. In other words, we have two objects multiplying to become 0, this guy and this guy. So therefore, either the first object is 0 or the second object is 0. Solving that first equation, you get x squared is equal to 2, or in other words, x is equal to plus or minus the square root of 2. Solving the second equation, you get that x is equal to a negative 2. So those are the values of x for which f of x is equal to g of x. You do have to evaluate functions symbolically, that means like at a k squared minus 1, quite often, and you do have to solve functions for specific values. So f of x is equal to 0, f of x is equal to 2, f of x is equal to g of x, stuff like that. That occurs more and more frequently as you move up the chain in mathematics. As a reminder, you should have seen piecewise defined functions. In fact, you have, but we'll just go ahead and remind you how they work really quickly. A piecewise defined function, which I write as a piecewise function, but I will almost always call them piecewise defined functions, is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of these smaller domains. A piecewise function in general has the following notational format. F of x is equal to, and then we use this brace right here to say this is a group of conditions. You have some first function that f will become if your input belongs to some specified interval. Otherwise, it becomes some second function if x belongs to a different specified interval, and so on and so forth, right? You can have more than 3 functions. You can have 2 functions, you can have 20 functions, you can have 1,000, okay? But the reality is that you're just breaking a function into cases. It's sort of like you saying, you know what, I'm gonna wear a red shirt if it's Monday, a blue shirt if it's Tuesday, a green shirt if it's Wednesday, that type of thing. It's an if-then situation. So here's a common looking piecewise defined function. F of x takes on 3 possible functions. The first function, x squared plus 3, well, f of x is going to equal that as long as we're plugging in values less than 2 for our inputs. F of x will be 7 as long as we're plugging in values of x greater than or equal to 2, but still less than 4. So numbers like 2.5 or 3.99 or 2. And finally, f of x is equal to this 2x minus 1 as long as x is greater than or equal to 4. Notice that our conditions here cover all possible values of x. So if you had an x value of 0, well, 0 happens to belong in this group right here. If you plugged in, let's say 117, well, that belongs over here. If you plugged in pi, that belongs right there. Just letting you know that not all piecewise defined functions need to be defined over all real numbers. In other words, it could be the case, for an example, that our function could only be defined for positive values of x. So in other words, this only works for x between 0 and 2, then between 2 and 4, and then greater than or equal to 4. And notice you do not have a description for x if x is less than or equal to 0. That just means your function doesn't exist for x less than or equal to 0. But that wasn't the case we were handed, so let's just ignore that. Now let's go ahead and evaluate this function at 0, 3, and 4. F of 0. Well, 0 is definitely less than 2, so we're just going to plug 0 into the top function. F becomes 0 squared plus 3, or in other words, 3. If you're to plug in 3, 3 belongs to the second group because 3 is between 2 and 4, and the function, when you plug in 3, is always 7. There's no x value there, so there's nothing you need to plug x into. It's just an output of 7. It's a constant. If you were to plug in 4, well, 4 belongs in this group right here because 4 is greater than or equal to 4. In this case, we'd get 2 times 4 minus 1, or 7. And that's how you would evaluate a piecewise defined function. They're actually not too terrible. Where do you see piecewise defined functions? Like all over the place in the real world. They are very, very common. So a marginal tax system, this is a good example of one, like the one we have in the US, is where a taxpayer pays a specific percentage of their income to the government, but this amount changes at certain levels. For example, the USM, which is the United States of Mathematics, has a system where each individual pays 0% for the first $10,000 they earn, but then 10% per dollar thereafter up to $36,000, and then at that point they pay 25% per dollar earned thereafter until they reach to $100,000 in income, and then finally after that they just pay 50% of every dollar they earn. So building a piecewise defined function for this tax system is somewhat daunting. We'll start by just creating a function name. Let's call t of x the amount of tax that you owe based upon the amount of income that you earn. So again, we're going to let capital T be the amount of taxes owed and let x be the annual gross income, the amount of money that you make before taxes are taken out. Then the amount you owe in taxes is defined by one of several different possibilities. And I like to write down the possibilities first. So our possibilities are we earned less than 10,000. The next possibility is that we earned between 10,000 and 36,000. The next possibility is that we earned somewhere between 36,000 and 100,000. And finally, the last possibility is basically if you earned anything over 100,000. So let's go ahead and write those possibilities down. It's 4 different groups. The first group is if the amount we earn is less than 10,000. Now I need to check if it's less than or equal to. So let's read that sentence. For example, the USM has a system where an individual pays 0% for the first $10,000 they earn. So I can earn up to $10,000. And in that tax bracket, I will not pay any money in taxes. That's $1 right there. And now the second group means that you earn between 10,000 and 36,000. So let's see. That's this part right here, but then pay 10% per dollar thereafter. So starting at 10,000 and up to 36,000. So I'm going to say that includes 36,000. So the next group will start at $10,000 and go all the way up to $36,000. Notice I'm not including $10,000 in the second group because it's already included in the first group. The next condition means that we've earned more than 36,000, so we might as well just write that in. And we got up to possibly $100,000. That's this right here. And the final group of earners just earn over $100,000. So that's the beginnings of a piecewise defined function for this very special tax system. Just to let you know, our tax system in the United States is very similar in build to this. It's not exactly the same because the percentages and the numbers are slightly different, but the build is almost identical. So how much tax do you owe if you earn less than $10,000 or less than or equal to $10,000? Well, in this system, an individual pays 0% for the first $10,000. So let's just write that down. Often you'll see a comma separating those things. So the amount you owe in taxes, if you earn less than $10,000, less than or equal to $10,000, is 0. Now let's move on to the next tax bracket. So we have 0% for the first $10,000 we earned, but then we pay 10% per dollar earned thereafter up to $36,000. So a lot of people would say, oh, great, you pay 10%, which as a decimal is 0.1, of every dollar you earn. But that's not true. You do not pay 10% of every dollar you earn. You pay 10% of every dollar earned beyond $10,000. So for example, let's pretend that you made $11,000. If this were the formula, then you would owe 10% of 11,000, which is $1,100. But that's not true. The first 10,000 you're not taxed on. You're only going to be taxed on the extra 1,000, the extra 1,000 above 10,000 that you earned. So you don't want to pay $1,100 in taxes. You're actually only supposed to pay $100. So what we're going to do is say, well, you pay 10%, but that 10% is on what you made over $10,000. Try that out. Plug in 11,000 into that. If you made $11,000, 11,000 minus 10,000 would be 1,000. 10% of 1,000 would be $100. So you would pay $100 in taxes if you earned $11,000 in salary. And that is because the first $10,000 you do not need to pay a penny on. Now let's go to a slightly more complicated case. After that point, we now pay 25% per dollar earned until we get to $100,000. That is, once we reach $36,000, the next dollar I earn, I pay 25 cents of that in taxes. And again, this is the US tax code. So let me just say, a lot of people again will say, okay, well then I'm paying 25% of what I've earned. That's not true. You pay 25% of what you earned beyond $36,000. Now that's not the finish. You're not done with this, but that's the amount you would pay for every dollar beyond $36,000 in income. However, you have to include in this all the money that you paid in the previous tax bracket. So you earned $36,000 minus $10,000 or $26,000 while you were in this specific tax bracket right here. So you earned $26,000 and you were paying 10% on each dollar in that $26,000 area. So you will have paid 10% of $26,000, which is $2,600. And actually, that using the previous tax bracket idea actually works here as well. We used our previous money that we paid for the previous tax bracket there, and then we included 10% of what we earned here. Then we used the $2,600 we paid in that tax bracket there, plus all this money that we earned between $36,000 and $100,000. Finally, when you get to greater than $100,000, you're paying 50% per dollar earned thereafter. That is, if you earn $100,001, that one extra dollar, you pay 50 cents in taxes. So you only actually are earning 50 cents, not a dollar. So just like we've done previously, I'll go ahead and say the amount that we pay in taxes in this bracket is 50% of whatever we earn above $100,000. Plus, we need to include all the money that we paid at 25%. And we paid 25% of the $64,000 we earned in that category. So again, we earned $64,000 while being in the 25% tax bracket. So we need to compute what is 25% of $64,000. And that is $16,000. But that is only what we paid while we were in the 25% tax bracket. We still have to include the $2,600 that we paid while we were in the 10% tax bracket. So this is a very big example, but a really good example to showcase how piecewise defined functions actually work in the real world. I'm not going to simplify the mathematics here or combine anything. I'm just going to leave this as written. I think this is a tough problem normally, but you're in a college algebra course, so you should be able to kind of build stuff like this. As our final example, we're going to use the graph of a given function to answer some questions. And these are generally found in any algebra course, like an Algebra 2 course or something like that. So our function here is named g. That's what this function is right here. And we're being asked in part A to evaluate g at 0. that means that we're going to let x equals 0. And we want to find out what the output is for our function. So if you look at our axes here, x equals 0 is right here. The value of the function, assuming these are all 1, 2, 3, right? Assuming these are all single scaled by 1 unit at a time, the output when we plug in 0 for the function is going to be 2. So g of 0 is equal to 2. That shouldn't be too terrible, but a lot of people mix that question up with question B. Solve g of x is equal to 0. G of x equaling 0 means we want the height of our function, the y value of our function, to be 0. And if you take a look at this curve, the function reaches a height of 0 right around here. And if I zoom in, let me actually label my axes. If you zoom in a little bit, you can see that's a little bit beyond -3, maybe like a -3.2. So solving g of x equals 0, we could say that implies x is approximately -3.2. That's very roughly -3.2. We're not 100% sure, but it looks right. And then finally, solve g of x is equal to 1. Again, that's like saying when is y equal to 1? So if I look at my curve here, the height of 1, well, our curve reaches a height of 1 right about there. Our curve also reaches a height of 1 right about here. I would say that's probably 3. And it reaches a height of 1 at, what is this, 4, 5, and 6? 6. So there are 3 spots where our curve reaches a height of 1. It's roughly about a -2.2, and I'm going to say roughly 3, and also 6. That question shouldn't be new to you if you've already seen functions before, which you should have, so it just should be a good reminder of how that stuff works. All right, we're completely done with this video on a review for evaluating functions for college algebra. The next video will focus on one-to-one functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.